The machine that built civilization. Long before rockets pierced the sky, before computers shrank into pockets, before engines roared and factories screamed with motion, there was a quieter miracle turning in the shadows of human progress. It did not glow. It did not explode. It did not look impressive to an untrained eye. And yet, without it, almost nothing modern would exist. This is the story of the lathe, the most important machine humanity has ever built, and the absurdly precise engineering obsession that turned a spinning stick into the foundation of civilization itself. At its core, the lathe is deceptively simple. One object spins, another object cuts. That's it. No magic, no electricity required, no advanced materials, just rotation and resistance. And yet, that simplicity hides a brutal truth. Nothing in engineering is more unforgiving than rotation. When something spins, every error is magnified. Every vibration becomes a scream. Every microscopic misalignment becomes a catastrophe. And still, human beings bet the future of technology on this idea, that we could spin matter and shape reality itself. The earliest lathes appeared thousands of years ago, powered not by motors but by human muscles and patience. Ancient craftsmen used rope and bow lathes to shape wood, bone, and soft metals. One person pulled the rope back and forth while another held a cutting tool steady, praying their hands wouldn't slip. These machines were crude, unstable, and wildly inconsistent. But they revealed something profound. If you can control rotation, you can create symmetry, and symmetry is power. A round shaft fits into a round hole. A smooth cylinder rolls instead of scraping. A balanced object survives stress that would shatter irregular shapes. Civilization noticed. As societies grew more complex, so did their demands. Carts needed axles, ships needed pulleys, weapons needed straight, balanced components. Empires don't fall because of philosophy, they fall when logistics fail. And logistics depend on parts that fit together reliably. This is where the lathe quietly began to outgrow kings, armies, and monuments. It wasn't about beauty, it was about repeatability. The radical idea that you could make the same thing twice, and it would actually be the same. But repeatability is a nightmare in the physical world. Materials resist uniformity. Wood warps. Metal hardens unevenly. Heat bends things invisibly. The lathe demanded engineers face an impossible question. How do you force chaotic matter to obey geometry? The answer was relentless precision. Better bearings, straighter spindles, harder cutting tools, more rigid frames. Each improvement exposed new problems. Fix vibration, and heat becomes the enemy. Fix heat, and tool wear ruins accuracy. Fix tool wear, and alignment errors surface. The lathe became an endless battle against physics itself. By the time of the Industrial Revolution, the lathe had transformed from a craft tool into a strategic weapon. Steam engines needed perfectly round pistons. Cannons needed straight, concentric barrels. Early factories discovered something terrifying. Even the most brilliant design is useless if you cannot manufacture it accurately. The lathe didn't just support industrialization, it defined its limits. Engineers didn't ask, can we imagine it? They asked, can we turn it? This is where the engineering becomes ridiculous in the best possible way. To improve accuracy, engineers began chasing tolerances smaller than human senses could perceive. They built machines whose only purpose was to build better machines. Lathes were used to make parts for even more precise lathes, in an infinite loop of self-improvement. It was engineering recursion, a philosophical absurdity turned mechanical. Reality, the machine that builds itself better over time. And yet, the lathe is merciless. Unlike digital systems, it offers no forgiveness. There is no close enough at high speeds. A micron of error becomes vibration. Vibration becomes tool chatter. Tool chatter destroys surface finish. Poor surface finish causes friction. Friction causes heat. Heat causes expansion. Expansion destroys tolerances. One small mistake triggers a chain reaction that ends in failure. Every successful lathe is therefore a monument to engineers who understood that perfection isn't optional, it's survival. By the 20th century, the lathe had quietly infiltrated every corner of modern life. Engines, turbines, generators, medical devices, aircraft components, all passed through its spinning jaws. Even machines that don't look round at all often begin as round stock, shaped by rotation before being cut into complexity. The lathe became the silent gatekeeper of technology. If a design couldn't survive turning, it didn't deserve to exist. Perhaps the most astonishing part is this. Even today, with CNC machines, AI optimization, and laser measurement, the core principle hasn't changed. Something spins, something cuts. Physics watches closely. Engineers still fight the same enemies: vibration, heat, alignment, material inconsistency. The tools are more advanced, but the challenge is eternal. The lathe is not outdated. It is undefeated. And this is why calling the lathe just a machine misses the point entirely. It is a philosophy made of steel. A declaration that humans will impose order on chaos, even if it takes centuries of iteration. It is proof that progress doesn't always arrive with explosions and applause. Sometimes it arrives quietly, spinning, shaving away reality one fraction at a time. In the next part, we will dive into the absurd engineering problems that nearly broke the lathe, the vibrations that destroyed factories, the tolerances no one believed were possible, and the failures that forced engineers to rethink what precision even means. The war against vibration, heat, and reality. If part 1 was about why the lathe matters, part 2 is about why it nearly broke engineers' sanity. Because once humanity committed to precision, the lathe stopped being a simple tool and became a battlefield. Every rotation exposed a new enemy. Every improvement revealed a deeper problem hiding beneath the surface. The lathe didn't fail loudly. It failed subtly, invisibly, and relentlessly, punishing even the smallest mistake with catastrophic consequences. The first great enemy was vibration. To the untrained eye, vibration looks harmless, a faint shudder, a quiet hum. But in machining, vibration is destruction in slow motion. When a workpiece spins, any imbalance creates oscillations. Those oscillations amplify through the machine's frame, bounce back into the cutting tool, and explode into a phenomenon engineers call chatter. Chatter isn't just noise. It's a feedback loop where the tool starts hammering the material instead of cutting it, leaving ripples on the surface that make precision impossible. Once chatter begins, accuracy collapses. And early lathes were basically vibration factories. Engineers tried everything: heavier frames, thicker cast iron beds, slower speeds, stronger mounts. Each solution fixed one problem and created another. Make the machine heavier, and it absorbs vibration, but now it's harder to align, harder to transport, and more expensive. Slow the spindle, and vibration drops, but productivity dies. Increase rigidity, and cutting forces rise, accelerating tool wear. The lathe became a balancing act so delicate that entire careers were spent adjusting a single variable by fractions of a percent. Then came heat, the quiet killer of accuracy. When metal is cut, it heats up. When it heats up, it expands. When it expands, your perfect dimensions vanish. This is where the lathe exposed a cruel truth. Even if you machine something perfectly, it won't stay perfect. A shaft measured hot will shrink as it cools. A bearing bored cold will expand during operation. Engineers had to stop thinking in static dimensions and start thinking in thermal timelines. Accuracy wasn't about size anymore. It was about predicting how size would change. Cooling systems were introduced, but coolant created its own chaos. Uneven cooling warped parts. Coolant contaminated surfaces. Temperature gradients bent spindles just enough to ruin alignment. Some factories discovered their lathes were more accurate in the morning than in the afternoon because the building itself expanded in the sun. Precision had become environmental. The lathe forced engineers to acknowledge that the earth itself moves and breathes, and machines suffer the consequences. Alignment was another nightmare. A lathe only works if its spindle, bed, carriage, and tool post exist in perfect geometric agreement. But perfect is a fantasy. Metal sags under its own weight. Bearings wear asymmetrically. Foundations settle. Even gravity introduces distortion. Engineers began scraping machine surfaces by hand, removing material atom by atom, to achieve flatness no casting process could deliver. This scraping wasn't artistry. It was survival. Without it, precision collapsed. And then there were cutting tools, the interface between intention and reality. Early tools dulled quickly, changing geometry mid-cut. A tool that starts sharp ends blunt, altering forces, increasing heat, and shifting dimensions. Engineers realized that accuracy depended on something absurd, predicting how fast steel would die. Tool metallurgy exploded in complexity. high-speed steel, carbides, coatings. Each advancement pushed speeds higher and unleashed new instability. Faster cuts meant more heat. More heat meant more expansion. The lathe never let engineers win. It only let them trade problems. Perhaps the most ridiculous challenge of all was tolerance. As industries matured, good enough stopped being enough. Interchangeable parts demanded tolerances measured in microns. Eventually, nanometers. At that scale, surface roughness mattered more than shape. A perfectly round shaft with microscopic peaks could seize in a bearing. Engineers learned that smoothness wasn't cosmetic, it was mechanical destiny. The lathe became a surface engineering machine as much as a shaping one. This obsession with tolerance led to an almost philosophical crisis. Measurement tools became as important as machines themselves. You couldn't improve what you couldn't measure. Micrometers, dial indicators, laser interferometers, entire industries were born just to verify that the lathe hadn't lied. And sometimes, the machines were right and the measurements were wrong. Engineers learned to distrust everything, including their own instruments. Factories began isolating lathes from vibration sources, mounting them on massive foundations, separating them from foot traffic, even controlling air temperature to within fractions of a degree. The lathe demanded silence, stability, and obedience. It punished chaos mercilessly. This is why truly precise machining environments feel more like laboratories than workshops. The lathe doesn't tolerate improvisation. And yet, despite all this, engineers kept pushing. Because every breakthrough, in engines, aviation, medicine, energy, depended on parts that could only exist if the lathe behaved. The machine became the bottleneck of progress. If engineers could tame vibration, heat, alignment, and wear just a little better, the entire technological world advanced with it. By the end of this war, the lathe had reshaped engineering culture itself. Precision became a mindset. Assumptions became dangerous. Margins disappeared. Engineers stopped trusting intuition and started trusting data, iteration, and relentless testing. The lathe taught humanity humility. It reminded us that physics always collects its debt, with interest. In the next part, we'll explore how this brutal machine didn't just shape metal. It secretly shaped the modern world, influencing how factories were organized, how standards were defined, and why almost every advanced technology traces its lineage back to a spinning axis. How a spinning tool quietly took over the world. By the time engineers began to believe they had finally tamed the lathe, it was already too late. The machine had escaped the workshop and rewritten the rules of civilization itself. What began as a tool for shaping simple cylinders had evolved into the invisible architecture of the modern world. Not through spectacle, not through force, but through standards, repeatability, and a ruthless demand for sameness in a universe that naturally resists it. The lathe's greatest victory was not mechanical, it was cultural. Before precision machining, craftsmanship ruled. Every part was unique, shaped by the hands and judgment of an individual. Repairs required the original maker or someone equally skilled. Complexity scaled poorly, but the lathe introduced a heretical idea, that parts could be anonymous. That a component made in one place could fit perfectly into a machine made somewhere else, by someone who would never meet the original machinist. This single shift unlocked mass production, global supply chains, and modern industry. Standards were born from spinning steel. Thread forms, shaft diameters, bearing fits, all trace their ancestry to what lathes could reliably produce. Engineers didn't choose standards arbitrarily, they were negotiated compromises with physics. If a tolerance was too tight, scrap rates exploded. Too loose, and machines failed. The lathe defined the narrow corridor where industrial sanity lived. Entire nations aligned their measurement systems around what their machines could actually hold. This quiet revolution reached its peak during the industrial and wartime eras. When wars demanded weapons by the millions, hand-fitting was no longer possible. Interchangeability wasn't a luxury, it was survival. Rifles had to accept any bolt. Engines had to accept any piston. Vehicles had to be repaired in the field using parts made thousands of kilometers away. The lathe made this possible by enforcing geometric obedience at scale. Without it, industrial warfare, and modern logistics, would collapse. But the influence went deeper than factories. The lathe reshaped engineering education itself. Students were no longer trained only to design, they were trained to design for manufacturing. Ideas that couldn't survive turning were rejected early. This feedback loop disciplined creativity. Engineers learned that elegance wasn't just theoretical beauty, it was manufacturability. The lathe became the silent critic of every blueprint. Then came automation, copying lathes, tracer lathes, and eventually CNC machines transformed human skill into encoded motion. What once lived in the hands of a master machinist moved into CAMs, templates, and later, software. This was not a loss of craftsmanship, it was its amplification. A single program could now express precision millions of times without fatigue. The lathe didn't eliminate humans, it multiplied them. CNC lathes pushed the absurdity even further. Tools move along multiple axes with micrometer accuracy, guided by mathematics and feedback. Systems operating faster than human perception. Yet despite the digital sophistication, the core vulnerability remains unchanged. Vibration still lurks, heat still distorts, tool wear still lies. The computer doesn't solve these problems, it negotiates with them. Even the most advanced CNC lathe is still locked in dialogue with physics. The lathe's fingerprints are everywhere. Jet engines rely on shafts that must survive extreme rotational stress. Power grids depend on generators whose rotors are turned to near perfection. Medical implants require surfaces so smooth they integrate with the human body. Even the devices that design other machines, computers themselves, contain components born on lathes. The machine that makes machines is not a metaphor. It is literal. Perhaps the most ironic twist is this. As technology advanced, the lathe became less visible, not more. Clean factories, enclosed machines, automated tool changes. To outsiders, the drama vanished. But behind the safety doors, the same ancient struggle continues. Rotation versus chaos, precision versus entropy. The lathe still decides what is possible. And it does so quietly. No one applauds a perfectly turned shaft. No headlines celebrate a micron held under thermal load. Yet entire systems depend on those victories. When a turbine runs smoothly, when an engine lasts decades, when a satellite survives launch, the lathe has already done its work. In the final part, we'll confront the ultimate question. Why humanity is still dependent on this ancient idea, why no futuristic technology has replaced it, and why the lathe may remain essential for as long as civilization relies on machines at all. The machine humanity can never escape. Every era believes it is on the edge of replacing the past. Stone yields to bronze, bronze yields to iron, analog yields to digital, and yet, beneath every illusion of progress, the same truth waits patiently, spinning. The lathe has survived not because humans failed to invent something better, but because rotation is unavoidable. As long as machines move, carry loads, transmit power, or resist friction, something must be round. And as long as something must be round, the lathe will exist. This is the uncomfortable realization engineers eventually reach. No matter how advanced our tools become, matter still obeys the same laws. Atoms do not care about ambition. Metals still expand when heated. Forces still propagate through structures. Vibrations still amplify. The lathe endures because it addresses reality at its most fundamental level. It doesn't fight physics. It works with it, exploiting symmetry as nature's most stable compromise. Even the most futuristic manufacturing methods eventually circle back to the lathe's logic. Additive manufacturing can grow shapes impossible to machine, but those parts still require finishing. Bearings still need precision surfaces. Shafts still need concentricity. Interfaces still demand smoothness and alignment. 3D printing did not kill the lathe. It exposed how irreplaceable it actually is. The more complex designs become, the more brutally precise their interfaces must be. This dependence becomes terrifyingly clear in high-stakes engineering. Aerospace components experience extreme rotational forces. Medical devices must survive inside human bodies without failure. Energy infrastructure runs continuously for decades. In these domains, tolerance is not negotiable. Failure is not dramatic. It is silent and irreversible. And in every case, engineers trace reliability back to one question: was it made accurately enough? The answer almost always leads to a lathe. There is also a deeper, almost philosophical reason the lathe persists. It embodies feedback. Unlike many machines, the lathe constantly tells you the truth. Surface finish reveals vibration. Tool wear reveals thermal imbalance. Dimensional drift reveals structural weakness. You cannot lie to a lathe. It exposes mistakes immediately, often violently. This makes it a brutal teacher, and an honest one. Entire generations of engineers were trained not by textbooks, but by watching parts fail on a spinning axis. In a strange way, the lathe shaped human character as much as human technology. It rewarded patience. It punished arrogance. It forced humility in the face of microns and milliseconds. Engineers learned that mastery was not dominance, but listening to sound, feel, heat, and subtle change. This mindset spread outward into other disciplines. Precision engineering became a worldview. And so, the lathe remains, not as a relic, but as a backbone. Hidden behind enclosures, buried inside supply chains, uncelebrated yet indispensable. Civilizations don't collapse when monuments fall. They collapse when maintenance fails. When tolerances drift. When parts no longer fit. The lathe stands between order and that slow, grinding decay. The most ridiculous part of all is this. Humanity's grandest technologies still rely on the same principle discovered thousands of years ago by someone pulling a rope around a spinning stick. We've added motors, computers, lasers, and code, but we never escaped the original idea. Rotation plus control equals power. Everything else is decoration. The world's most important machine is not the fastest, the largest, or the smartest. It is the one that quietly makes all others possible. The one that demands perfection while knowing it can never truly be achieved. The one that keeps turning, indifferent to trends, waiting for the next impossible idea to be made real. And as long as humans build machines, the lathe will be there, spinning, shaving, enforcing reality, reminding us that progress is not magic. It is discipline, repeated endlessly, one rotation at a time.